And well, before we get started, let me remind you that we are going to have a makeup class this Wednesday at 6:30 because next week I will be in. I was invited to USA for a speech. So next Monday there is no class. The class in next Monday is moved to this Wednesday, 6:30 to 9. All right. So if you happen to have a break, please come over here to be with us. And then the last lecture will be May 29th. The last lecture. So a total of 3 lectures are left. Then there will be no class on June 5th, all right, as we discussed before, and the final exam will be in June 12th. June 12th, okay? It will be an open book test, okay? You are welcome to bring any paper with you, okay? So that hopefully those papers can help you to pass the exam. That's about everything I want to say today. So that's it. So we will have a break around 10:25, right? Okay. So let's get to it. Do you understand what I say? Okay. Today of course, we are going to have a lecture, and the next week I will be in USA, okay, to give a speech in the conference. So that the class next Monday will be moved to this Wednesday evening, and then after I come back, I will give the last lecture of this semester, which will be May 29th, okay, and then on June 5th, there is no class because that's one of the extra 2 weeks of the school. However, I will ask my TAs to give a TA recitation then to answer all the questions in your mind, in the homework, in the midterm exams, and then help you to prepare the final report submitted to TSI for your chip takeout. And then the final exam will be June 12th. Okay, that's it. That's about everything. Okay, and this is what we were last time. Okay, we talked about dynamic logic. Then, excuse me. And we discussed the single rail, and then we stopped before the dual rail. And the rest of the dynamic logic is just a legend. Okay, what do you mean a legend? Because in my 30 years of career of VLSI design, almost zero students to carry out dynamic logic. Okay, just a few. And only one of the dynamic logic was physically tape out the chip and publish papers. I'll tell you what that is, okay? And the rest, as I say, they're just legendary things. And technically speaking, or I should say theoretical speaking, they are really good in terms of performance. But it will become really hard, okay, to realize it and measure the performance because there's so many teeny tiny things, so many details you have to take care of. Otherwise, you won't see nothing, okay, on the chip measurement. Okay, then let's get to it. I will spend some time to explain to you so that we can wrap this up before the end of this lecture. So dual rail logic domino. As we emphasized in the previous lecture, that domino is probably the best of the single rail dynamic logic. Okay, dual rail, it's similar to what we discussed about the dual rail static logic. Okay, basically you're going to have pair of inputs, x plan, y plan. Okay, you have the true and the complement inputs simultaneously go to 2 boxes. Okay, one is for the F, the other one is for the F bar. And the only difference between the dynamic logic and the static logic is that, okay, the charge and discharge is controlled by a single clock, so that you see that there is a first switch over here, controlled by the clock, and there is another pair of PMOS transistors on the top, okay, which will be turned on when the clock is low, okay, to pre-charge F and a bar simultaneously. So this is dynamic dual rail domino logic, and the right-hand side is an emphasized version. Okay, what do I mean about emphasized version? Because remember last time we said when you see a pair of P latch back to back sitting next to each other, they are called the latches. Okay, and this is very good to keep the charge over here, so that the charge sharing or the fading of the voltage, okay, attenuation of the voltage can be prevented. Okay, it is just like the circuit that we emphasized before. Remember the last time we talked about this? And we were so afraid that the voltage here, this is just a C load. The voltage here, okay, when the clock is low, when the clock is low, that is one is off, then it's pre-charged. It's pre-charged, okay, it's pre-charged. Then after the pre-charge is fine. But the thing is, after the pre-charge, okay, this is when it's blocked, and this is on. Then some shitty things happen. Okay, for example, if you are doing the NAND design, then very likely this one is used to block the bottom transistor over here. This one will turn down. Then there is a risk. Some of the charge over here will be shared with some parasitic capacitor over here, so that the voltage here will be dropped. Okay, it is called a charge sharing. So to prevent this kind of bad things happen, we emphasize that we can use so-called a keeper over here. So when this is 1, this will be 0. And turn on this pass so that some small current will be taken from the top to this point, and whatever is lost over here will be a pullback to the normal voltage level. This is a keeper. Okay, this is for the single rail dynamic logic. Okay, similarly, we can use a keeper over there, okay, for both paths, so that they become a cross couple over here. So this is emphasized version, okay, it's a strong version or enhanced version of the normal one. Okay, it's up to you whether you want to use that cross-couple P pair to become the charge keeper. So this is dual rail dominant logic, okay? And those P transistors sitting in the shadow area, the size is much smaller. Okay, they cannot become a strong current competitor with the normal operations. Okay, they have to be small. Small does not mean the width is small. It means the length of that two keepers is longer than normal transistor, just like this one over here. This one cannot become a competitor with the normal operation over here. So basically, this one is going to drain a little bit of current, supply a little bit of current to keep the charge here stable. So the length of this one is longer. That means it's a long transistor, and which is going to supply small currents. Okay? So this is a dual rail dominant logic. Okay? And this is just an example to show you how it works. Okay? So basically, you can see what is the function over here. Okay, it's pretty to be understood. X and X, Y bar. You check this out. I'm not going to redraw it on the board, so I'm going to tell you what the function is. So we check the box, the big box over here. Okay, the big box, this is for the operation on the other side. So you check over here, what is the ground path? This is how you check it out. What is the ground path? Let's assume the clock is high. So when this is high, there is no problem at all. So X and Y bar, you have two terms. X and Y bar. This is one of the paths to ground it. Okay, what happened to the other one? X excuse me. And the other one is X bar goes through the Y. So that will become this way. So basically, either of these function becomes 0, that point will be grounded. Okay, here, let's assume this is F. So the F will become this way. Okay, the F. If the voltage symbol at this point, so either one of them, so if this one is pass, that means when this is high, okay, then the Boolean function will become 0. Or the other pass, X bar and Y is over here. Okay, this is where the F is. The F is sitting over here. This is where the F is. Okay, so what is the function here? Apparently, the function over here will become the F bar. That is bar and a bar, because we're inverted over here. That will become this way. So this is apparently the definition of exclusive OR. Okay, that's it. So this is how you analyze what the function is. Okay, that is left side. So on the other side is definitely the dual function of the left-hand side. So that's become exclusive norm. You can go home and check it out. Okay, so this is what the function is. I have to trace it. So what about an N? An N. It's the same thing. Okay. See? It's the same. Here, this is very simple. What is this? This is a parallel, right? And this is serial. So the A and the B, apparently. When this one both are high, this will become NAND function. Here, they become the N because we have an inverter over here. Okay? So that'll be N, there'll be NAND. So guarantee they must be dual. Okay, they must be dual. So one side is complement, the other side is true. And the networking, the M box or M block, they are dual. Okay. So the pull-down networks are conditional, are conduction complements. All right, and then we are going to different kind of a dual rail dynamic logic. This is called the CVSL. It's a long name. CVSL. So, ladies and gentlemen, check this out. See, guaranteed that it looks similar to the domino logic. See, we have a F block and an F. We have a foot switch over here. Then we check left-hand side first. The only difference that we don't have is what? The inverters. They don't have an inverter, that's all. Okay? And the right-hand side is another strong, enhanced version. So in order to prevent the charge sharing effect, we have another pair, another P pair, cross-couple P latch, okay, sitting in the middle of this circuit. That is that provides the same function like the one we just talked about. Okay, it is used to increase the voltage on the F and F bar. That's all. So this is another version. The only difference that you can see from that picture is there is no inverters on both of the outputs. That's all. So, and this is, somebody used this as published papers. That's fine. Okay. And this is another one, okay? This is another one. Basically, it is the same as a domino, okay, a dynamic logic. The only difference is here. In the yellow box, use a sense amplifier. And what is a sense amplifier? Because that it's not a P latch. It is a pair of inverters back to back sitting next to each other. Okay, what is this? This is very useful stuff. I'm going to use this for you to tell you how to emphasize or increase the swing of your outputs if you are going to use a differential differential logic. Okay, so let's assume you have x and x bar. You want to do whatever function is, okay? Whatever function, I don't care, okay? As long as it's a dual, and then you want to make sure that x and x bar, they are going to have a full swing. Full swing, that means, okay, you want to make x 0 to VDD. Simultaneously, you want the x bar to have VDD and 0. Okay, we call that a full swing. That means the signals on either one is going to up and down, from the floor to the ceiling, okay, very perfectly. So, however, there are noises. Noises everywhere. Just like on the newspaper, you always see a lot of weirdo or bad guys in the society. They want to create some problems that damage the public transportations, okay, or accidentally breach the law. So what we do, okay, if we do have a pair of outputs like this one, and we like to have the functionality or the quality of the signal, so basically we do this, okay, we are going to use a pair of inverter, okay, and this is the best strategy. This is the way we do that. Why is that? Because when you have a signal here is high, right? Then on the other side of this inverter will become a 0. And the 0 will go back, okay, to the other side to become 1. So as soon as that, even though that the signal quality originally on both of the output is not that perfect, but after you add this, this inverter pair, okay, back to back, okay, they will help you to enlarge the difference, okay, enlarge the difference of both of the voltage on both sides, okay, that become a loop over here, and this loop is so lovely, okay, that it will faithfully execute the function that you like to increase the difference of the voltage on both wires, okay. The only problem that it creates is what? Okay, it will slow down the speed. Because the more devices you add at the outputs, that means the more capacitance, okay, more RC delays. So you got to pay something. This is what you're going to pay. You are going to lose some sort of speed performance. But what you get, you are going to get a signal quality, okay, signal integrity, thanks to the addition of this pair of inverters. So this is the same thing over here. It is called the sense amplifier, but this is a wrong name. The sense amplifier, in fact, has its own official definition. Okay. Anyway, we use that. Okay, sense amplifier, dynamic logic. It is very helpful to attain the signal integrity. Okay, and the last member of dynamic logic is called a clocked dynamic logic. So basically, we introduced that in the basic one, the single rail, the dual rail. Then the last the last family member is over here. It's called the clocked. A clocked dynamic logic. Then you might wonder, say, sir, we already have clock control dynamic logic, and the clock is used to control the foot switch and the charging P device. So why do we need another type of clock dynamic logic? Well, there is a slight difference, or slightly difference. Okay, there are so many of them. Basic one, NORA, MP domino, true single phase TSPC, okay, ON logic, and differential NORA. Okay, 1, 2, 3, 4, 5, 6. 6 sub-members. Okay, 2 of them are critically important because some of my previous students carried them out and measure it. It works. The first one is TSPC. And the second one is ON logic. Excuse me. It's very dry this morning. Okay, so let's get to it and introduce every one of you one by one, then you get to know what that is. Okay, so this is a fundamental, the basic type of clock CMOS. Okay, very funny, very interesting. Okay, there's a low, of course. So do you see a big difference between this kind of clock dynamic logic versus the previous one? You see that the control, the transistor controlled by the clock and the clock bar are sitting in the middle, okay, of the circuits, okay? And then in the middle of the clock and the clock bar is the output. And the inputs, they are parallelly, okay, either a true or true and the complement will go to either one of the blocks, okay, P block or N block, okay, to become the function F bar and F over there. So, well, at the first glance of this circuit, you see that, sir, this is a gigantic monster because all of the eliminated P devices are back. So the circuit will become very large. Is that true, sir? My answer is yes. Okay, my answer is yes. So, of course, it is not that welcome. Okay, but this is a very typical clock CMOS logic. And as I said, there are 6 members. So the other 5, okay, are the improved version of this one. But however, you got to give the credit to the first one who developed these circuits. It's quite smart, okay? And it is very, very impressive in terms of speed performance. Okay, so let's use one simple example, an inverter, to explain how it works. So let's check this over here. So let me redraw it on the board so that you understand how the operation is carried out. Okay, so this is basically an inverter. This is dynamic. This is a symbol of it. Okay, this is COK. Okay, how it works. Okay, this is how it works. So I copy the circuits from the from the screen to the board, okay, to see how it works. So let's find out what happened. Okay, so COK 0 and 1. So what's gonna happen? It's clocked. So it's slightly different from the dynamic logic. When the clock is 0, then this is 0, right? And this is 1. So both of them are off, right? So then V in, the signal comes over here, will be evaluated, okay, will be used to decide the status of these two. So when this is 0, the entire operation, this is off. Okay, nobody moves. And then suddenly, when this is 1, that means this is high, this is 0. Both of them are on. So when this is 1, the entire circuits will become this way. will become a typical inverter. So when this is off, nothing moves. Nobody moves, okay? But when the clock is on, is high, then you can consider, or you can presume that both of them are on, then it becomes nothing but a short circuit, so that the entire circuit is reduced or evolved into a pure inverter. That's it. So the symbol over here is used to stand for this kind of operation. The inverter function, the inversion function, is physically controlled by the clock. When the clock is high, it works. When the clock is off, it shuts down. Okay, become an open circuit, nothing. Okay, so you can consider that when it is off, that entire circuit will become this way. Will become an open circuit. That's it. Is all right? Okay. So basically, clock CMOS, okay, take the advantage of one thing and one thing only. We use the clock to become the switch to control the function of these circuits. Okay, so based on the observation of this basic clock CMOS, we see a lot of funny things. Okay, so here, what is this? This is a conventional dynamic logic. This is conventional. See that? Conventional dynamic logic with a foot switch and a charging P transistor over there. Then at the output of this dynamic logic, instead of using a single inverter, we use what? We use a dynamic inverter over here. This is a dynamic inverter. So when clock is low, when clock is low, so when clock is low, this point here will be charged. Okay, this is block. This will be pre-charged. Then when clock is low, it's off. So this become a pure inverter. The functionality is just good. Okay, as good as we pictured. Then when clock is high, okay, that one is off, this one is on. So the dynamic logic goes to the evaluation phase. Then this is on, this become an inverter. Whatever happened here will be inverted here. Then the function is carried out faithfully. Okay, so this is how it works. So this is called the NORA, okay, NORA clock dynamic logic. Why NORA? NORA means that no output racing, no output, there is no racing. Okay, if you use the P block over here, then you got to use the same inverter over there. But you got to be aware that the output is here, okay, it's not the one over there. It depends on what kind of block you use, N block or P block. And this kind of design sometimes is referred as a C-square MOS latch. C-square means the first C stands for clocked. So the C-square MOS is called the clocked CMOS. Okay, the official name is this. All right, it's called the NORA, and somebody did invent these circuits and published many papers and earned his credit in the history of a circuit design. That's fabulous. All right, then, just like the NP domino, we can use the similar. We use the NP domino clock dynamic logic. So the P block, N block will be followed by P block, and then goes to the final clock inverter, or clock inverter. So this is how it is organized as a NP domino logic. It's just like the complementary dynamic logic we mentioned before. So it's almost the same. But the thing is, none of my students ever tried this one. Okay, none of my students try this one. Because the reason is very simple. The area of this P block is way too large. It's not worthy. Okay, if you want to do this cascading operation to carry out a certain function, we strongly, or at least we recommend that the conventional N block, okay, is preferred. Don't ever try to use a P block because not only just the area, the power is amazing. Okay, now we go to the two real dynamic logic that has been physically implemented, okay, on the silicon. Okay, this is called a TSPC. Okay, now this is cool. What is that? TSPC, there is a major difference between the TSPC and the clock, clock CMOS. Okay, if you pay attention enough to the screen, you'll see the difference. See that? Something is gone here. This guy. This guy has been eliminated. This guy has been discarded from the new circuits. Okay? Because after analyze it, find out this one is redundant. Okay? That's the inversion. Okay, on the other way, if you use a PMOS, the other the N transistor in the ground pass can be removed, and it will not affect the function at all. Okay. Besides that, because we take away at least one transistor in the output stage, not only we save the area, we also save the power. So it's a good thing. So this is called a true single phase. And why is that? Because we only use one clock over here. And this is another clock over here. So that means the clock, the loading of the clock is reduced. Okay, the more transistor the clock is going to drive, that means the load is large. So right now, not only we take away the area, the power of that device, we also reduce the load on the clock signal. So too many benefits. So that's why this one is highly recommended in reality. A lot of students use these two single-phase circuits to carry out a variety of functions. Okay, this is one, particularly the left side, because that's the NMOS space is much smaller. So this, you're going to see a lot of circuits, okay, based on this design. It's called the TSPC, two single-phase clock. Okay, and this one was developed by many researchers, including my team, my lab. Okay, it is called the OR-N logic. OR-N logic has a very special and interesting feature, is that check over here, see that? Okay, this is original design. 1, 2, 3. These are the circuits. These are the devices. These are the devices, just like those over here. Okay. So basically, the OR-N logic is another strong version. It is based on the TSPC. Then we add one more devices over here. Okay, this guy is called the accelerator. It is called accelerator. Okay, what is that? Okay, when the X is pre-charged, this is 1, right? When clock is 0. When clock is 0, this is off, that's fine. Okay, this is 1, this is 0, so MP1 will be on to pre-charge X to high. So at the pre-charge to high, this one is blocked, this one is blocked. Nothing happened, just like what we expected. It's in the pre-charge phase, nothing's wrong. Now the only difference is that this MP2 give a very interesting function. Now let's go to the evaluation phase. That means clock goes down. clock goes high. So that MP1 is blocked, and MM1 is on. So we start the evaluation of this thing. If this one is still blocked, X will not be affected, okay, because the the gate capacitance over here is double than before. So the voltage at X will not be changed easily. However, if the evaluation of M block is to be passed, then X starts to drop. Okay? X starts to drop. Now, funny thing happened. Okay? Funny thing happened. What is that? So when X drops to certain voltage level, these circuits, okay, will be turned on. So it becomes very interesting. When X starts to drop to certain threshold, I mean somewhere below the VTHP, then MP2 will be smoothly turned on because this one goes to 0, right? When it's low enough, this one will be turned on. So we are going to, okay, take some current from the power supply to charge Z over here. So this gives us another extra pass, okay, to charge the output. So this is called the speed up speed up device, or they call the accelerator. Okay, accelerator. It provides this X. These provide another positive feedback loop. This is a very important one. This is for the MP2. Okay, when it drops to 0, below certain drops to 0, MP2 will be on to charge Z. Okay, drops to 0, MN3 will be off. Okay, so this voltage here will be high. Okay, and when clock is 1, this is already high. So this F will become high. Okay, will become high. So it's going to help you that not only when it is dropped to 0, this is turned on. Of course, this is high, and we provide an extra pass to pull up voltage Z to be high, so that both of these two voltage will become high. So the F will be elevated much faster. So this has become the positive feedback. It's a very interesting circuit, and it works because we not only we prove it, and we provide another improved version to make it much more faster. It was developed about 15 years ago in my lab. And my team back then published 2 important papers in IEEE journal because we proposed another better version than this one. Anyway, it's called the ANT. If you go to the IEEE check, the ANT logic, it's slightly different from this one. I would say the enhanced version is all AND transistor. Okay? Because we don't like the PMOS in the middle. Instead, we develop another circuit using the NMOS as the accelerator to do the same function, and it is renamed as not an ANL. It's called the ANT, ANT logic. So I can personally guarantee that this one works, because too many, I think at least like 4, maybe to 5 graduate students implemented this as a function of this one. Recently, an Indian student take advantage of this one to develop the adder, which can operate to up to 2 gigahertz. Okay, it'll be very fast. Of course, it pays the price of power. Okay, and differential NORA, well, it is nothing but just the topping on the pizza. Okay, the pizza itself already tastes good. Then the topping make it much more delicious. So as you see that this is a previous dynamic logic, a dual rail dynamic dominant logic. Then at the output we add 2 extra inverters driven by the clock, out of phase clock. Okay, the same thing is called differential NORA dynamic logic. It's nothing, just as I said, this is a topping on the pizza. Okay, the real credit goes to the inventor of that dual rail dynamic logic. Okay, this is differential version. Okay, now before we close this lecture, I have to bring this to your attention. Is that the leakage? Okay, leakage is everywhere. Okay, just like the leakage in your house. The transistor is not perfect. Okay, and for those students who might go to the IC design or semiconductor business, and as you might notice that the CMOS technology right now is heading into the 1 micron, 1 nanometer, maybe 2 nanometers in no time, okay, because TSMC and Samsung and Intel, they all announced that they own the cutting edge technology in the CMOS, okay, 1 nanometer, 2 nanometer, 3 nanometers, so on and so forth. Right now, the best technology offered to universities in Taiwan is 16 nanometer FinFET. And why FinFET, not the planar? The difference between the FinFET and the CMOS process that we use, the CMOS that we process is called a planar, that everything is on the two-dimensional plane, okay? And the FinFET that the gate is vertical, is a three-dimensional structure. The major reason why the FinFET become the dominant force in deep nanometer process is that it can prevent serious leakage. The planar cannot stop the leakage. Okay, planar device, planar technology has its own limitation. So, but unfortunately, we have to stick to our planar CMOS from time to time because we are poor, and the government and TSI don't have enough financial strength to support everybody use the FinFET. Anyway, so we are going to use whatever we are able to use. So the leakage is another problem. This is a problem when you do the design, particularly if you are going to design the dynamic logic. So dynamic load floats high during evaluation. Transistors are leaky. Okay, leaky. Transistors not perfect. Okay, whatever you learn in the computer science or so-called switch logic in the first year of your career, the college, the freshman career. So everybody in those computer science, computer engineering, or the textbook in the freshman tell you that a transistor is perfect, the logic gate is perfect. In fact, they are not. In the viewpoint of an IC designer and semiconductor engineers, they are not because of leakage. And it is even worse when you use the dynamic logic. So the dynamic value will leak away over time. So it will drop, okay? And at a certain of time, when the voltage at the output is lower than the threshold, it becomes unknown, and then even worse, becomes ground, becomes zero. That's bad. So you got to use a keeper over here. This is the one that we talk about, use a keeper, okay? When this is high, and this is zero, coming back to turn this one on is a weak keeper, and the size here is much smaller. So the students might ask a question very directly, what is the size? What is the reference number? My answer is 10 times of the length. 10 times, that means the current is smaller. It will become the 1/10 of the normal current. So a lot of students ask about this. They want to give it a try, save some time to party. So the K here becomes 1/10. That means the length of this keeper is 10 times longer than the neighbor that it is sitting next to. Okay, at least. It becomes very, very small. The long, weak enough. So when the length here is long, that means it's weak. Okay, the resistance is high, so current goes down. Okay, so the current here will not be able to compete with the current giving over here. So this guy is going to become the auxiliary circuit. It is not going to become a competitor. All right, so this is the one that I have to bring to your attention. And the second thing is the charge sharing. Charge sharing happens from time to time, okay, because as you can see over here, that if this guy is accidentally turned on, then we have a risk that some of the charge will sneak into the capacitance over here. So this is the phenomenon you see from time to time in your simulation over there. So this is the load, and this is parasitic, okay, parasitic capacitors. So when A, okay, in the middle of evaluation from 0, okay, goes from 0 to high, then bad things happen. What is that? Then X here will be pulled up. X here will be pulled up, okay? X, and then Y, where does this charge comes from? Of course, it is drained from the output. So the output will be pulled down, okay? If it's pulled just a little bit, then it's fine. But the best thing is when the output load is small, and the parasitic capacitor is almost the equal magnitude with respect to the output capacitor, then you have a risk that, okay, the voltage at the Y will go down below the VDD minus VTHP, then you have a risk. It will be judged as unknown, all right? That's a bad thing. So what is the risk over here? This is mathematical derivation, all right? So this is Vx, Vy after the charge sharing. So we can do some math to make you understand how to do the estimation or prediction of the C load that you like to have, so that the charge sharing will not give you any problem. So let's check this out. So Vx equal to Vy after the charge sharing, okay, is equal to Cy over Cx. Okay, so let's use the 5-volt system. Now, right now, your CMOS point aiding is 3.3 volts. That's fine. Okay, also 5. So typically speaking, in the 5-volt system, okay, the VTH P or VTHN will somewhere close to 1 volt, or somewhere becomes 1 volt. So we don't want what? We don't want bad things happen. So after the charge sharing, that this one cannot go under 4 volt. If you go under the 4 volt, then we have a problem to recognize whether this is high or low. So the 4 volt here, so this must be 4. This is the worst case. Okay, worst case, this is 5. Okay, so the Cy it's very easy math. You can do. Okay, you move 5 over here, take this away. This is the worst case, the lowest rate that you can tolerate, the lowest number that the output can be recognized as high or low. It's about this ratio. Okay, it's about ratio. Then you can do some math. So that means it's very easy to estimate. you got to guarantee the output over there must be 4 times larger than the parasitic capacitance. Then you might have a very safe, okay, recognition of the output voltage. However, this is not something you want to take, okay? Because we are designer, we always consider about the worst case. So basically, we don't use this number. Why is that? Because it's too risky. Maybe a little bit of variation, then it will drop below the 4 volt. So technically speaking, we like to use what? We like to use this number. .9. Okay, because this is, I'm sorry, not 4.5. 4.5 volt. This is 5, right? So drop by half volt, that is okay. So if this is the case, then we are going to have 0.9. Okay? And then this is become 0.9, 0.9. Nine times, okay? So this is close to what? 10. So basically, I always tell my students, it's better for you to ensure the output load of any dynamic circuits, okay, has a 10 times capacitance over the parasitic one. Okay, then even if you have a charge sharing, you will be safe. Okay, you will be safe. If it's about 4 or 5 times larger, then you have a risk that, okay, the noise margin might be bad. And you have a problem to tell how big if it's not a 1 or a 0. Okay, another way to resolve this problem, but only a few students ever try this one. It's called a secondary pre-charge transistor. That means we don't use any extra device. We simply add another charge capacitance to charge the intermediate node of the N block. But this way is not appreciated, because if we want to do that, what if we have 10 transistors in the N block? That means we got to have 10 pre-charging transistors on the top. That's not acceptable. So basically, theoretically it will work, but in reality, nobody use it. Nobody use it. Trust me, nobody use it. All right? Theoretically, it will work. Okay, we add a secondary pre-charge transistors, and typically it is required to pre-charge every internal node. That is not acceptable. That is not acceptable. All right, this is secondary pre-charge. You know that somebody proposed this idea. And basically, all of these techniques, all of these design techniques that we introduced is that to prevent what? The noise problem. So noise is everywhere. Okay, the world is not perfect. The world is not perfect. The system is not perfect. Okay, students complain a lot. So are the professors. We always complain about how injustice about the systems, okay, how we are not well treated, how we are not equalized treated. Okay, as we understand, the system is not perfect. Well, stop whining. It happens. It happens. Every human being exists on the surface of this planet. Just what I said before, life is not fair. Of course it's not. Okay, and if you pay notice to what happened in society is that, okay, it is really hard for any man, any young man to struggle if young men were born in a poor family. Okay, I'm not saying you don't have any chance. I'm saying you have a slim chance to turn it around. Okay, because as you understand that you want to make money. The money is not everything, but the money is a very good standard to judge what happened. So if you already know that whatever job you have, as long as the job, as you are paid by the hours you work, remember this, okay? Any job you take, if you are paid by the hours you worked, okay, it's a dead-end job. Sir, what the hell you are talking about? Any job, if you are paid by hours, for example, those staffs in the 7-Eleven, they are paid by hours, right? Okay, they are paid by, okay, the income is linear proportional to the hours that the poor guy standing behind the counter. Or the taxi drivers, okay, their income is hyperbolically linear proportional to the hours the driver is sitting behind the wheel. Okay, if they don't sitting behind the wheel and cruising around the street, they don't get nothing. Okay, and for those staffs working in that administrative building, they have to come to work. Otherwise, they will not be paid. Okay, this kind of job, I call that this is this is a job, it's a pay by hour, just like a professor. Professor is not a decent job. I still have to work, according to the hours signed with the universities, because I have to give lectures. Okay, sitting in my office for a couple hours every week. I call this is the same job. Okay, remember this: the income is linearly proportional to the hours you spend. That is called a shitty job, because if you want to rely on this kind of jobs to turn the things around, that's really hard. Okay, of course you can do that. Some of the guys really successful to turn the things around. I got to give them the credit. But the thing is, okay, you might ask the next question. Okay, what is a job? Okay, the income is not linearly proportional to the hours I spend. Okay, I call that the investment, or the income after you're asleep. You gotta find a way to create income when you are sleeping. You see my point? When you are sleeping or when you are taking a rest, you still have income. That's the thing you like to create. What is that? Okay. First thing cross your mind is that investment on the stocks or the funds. Okay, and you say, sir, I don't have that kind of a luxury of money. Okay, that's what I say. Okay, if you're from the poor family, then you don't have that kind of weapon in your hand to create the income after you sleep. And another thing is that, okay, after you work hard for a couple of years, that you have some deposit or savings in your bank. Don't just, okay, waste it, because a lot of students or young men, they don't want to spend their money or their incomes on what? On something very flashy, okay, sports cars, okay, nice clothes, okay, jewels, decorations, okay, these are all consumables to me. Okay, when you spend your money that you earn very hard on a sporty car like a Lamborghini, okay, you are flashy. Okay, you are a guy on the street that everybody likes to watch. But the thing is, as soon as the wheels of that Lamborghini touch the ground, okay, the cost drops and it is a 1/4. You see my point? It becomes a used car, and the car does not increase its value, okay, along the timeline. It's impossible. Okay, it makes you feel good. Let's assume you have $1 million, $10 million, and you want to spend on a sports car, or you want to put it in a very reliable fund or the stocks. Think about that way. Okay, if you have more money, if you have very deep pocket, okay, the best way I can think of is to buy the real estate, buy land, buy house. Okay, then you can lease the land, lease the house. Then you still have the income after when you are asleep. That's the best way to do the investment. And for those rich guys, after I deal with those guys, I find out they play two games that poor guys can never think of. Okay, the first one is called a capital games. Capital game is use the money to earn money. The second game they play is a land game. Okay, use a lot of land, a house, land game. And this is how they develop the income after they are asleep. So you gotta use your money. You gotta use the money you earn wisely. Okay, don't just waste that on a lot of useless things, flash things. Okay, jewels. A lot of ladies over there, they like to buy the, Chanel purses. What the hell is that? I don't want to use the bad words. Okay. And the purses, you can spend like $200 million for that. Okay. It's just a bag. And bag to carry a lot of, your stuff, like a little wallet or napkins, this kind of thing. You want to spend like $200 million for that? Ridiculous, okay? When the bag, for example, Chanel, Coach, or whatever, okay? What else? Hermes, okay? And when I see the newspapers, a lot of, recently there is a celebrity, okay? She was crying on the screen, say that her purse is real, blah, 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 blah. So what the hell are you thinking, okay? If it's a fake one, the fake one, that's fine, okay? As long as the function is good, you can carry it back without leakage, okay, the bag is good to me, okay? I don't need no brand on that stupid bag, okay? The only thing matters to me is how valuable you are. You gotta make yourself a valuable person, okay? Valuable is not judged. Value is not judged by those decorations, purses, or cars. Value depends on, okay, how you can create the values. That's all. Okay, let's go back to the noise. Too many noises are everywhere. Okay, and well, dynamic gates are very sensitive to noise. That's the bad thing about the dynamic logic. If you compare the dynamic with a static one, static is just like old-fashioned guys. Okay, they are square, they are big. Okay, we don't care about the storms coming. We don't care about the big heavy rain. Okay, everything compared to the power supply gives to me is nothing on the silicon. So static logic is very immune to the threats of the noise, but unfortunately, dynamic is fast, but it's sensitive. So the output is floating, suspect of the noise. So where are those from? Too many, okay? Capacitive crosstalk, charge sharing, we just mentioned. Power supply noise is coupled from every direction, okay? Feed-through noise and many more, okay? So it's impossible to have a noise-free environment. So as a designer, you gotta take this kind of thing into considerations. Otherwise, your chip will work on computer, but it will not work on silicon. That's what I say to my students. Okay, number two, you got to be aware is the power. Because dynamic logic or domino logic, they all rely on the switches of the clock. So every time the clock switches, that means dynamic power is consumed. So it's very power-hungry design. Dynamic logic has very high activity factors because every time the clock switch jumps up and down, that means dynamic power is needed to make it work. So output value evaluation pre-charge. The output probability, the activity is 0.5 because it changes time. Every cycle, it changes one time, 0 to 1. So the activity factor is 0.1, that's guaranteed. Okay, so alpha, for clock transistors, alpha equal to 1. So the phenomenon or the consequence is that this kind of design is very power consuming. That is the big, well, perhaps this is one of the biggest drawbacks of the dynamic logic, power hungry. Okay, but this is the price you have to pay if you want high-speed circuits. Okay, that's the power. And then domino logic summary. So domino logic perhaps is the most welcome popular design. Domino logic is attractive for high-speed circuit. It's still using. Okay, right now, for example, in certain adder design of high-speed CPU, for example, the ARM CPU or certain FPGA CPU, they use this one. And it's at least 2 times faster than the static CMOS. Okay, but it faces a lot of challenges. Okay, monotonicity problem, leakage, charge sharing noise, okay? So you gotta deal with that. And it's widely used in high-performance microprocessors. Okay, it's still being used. Okay, trust me, it works just fine. Okay, most of the largely displaced by static CMOS now power is a limiter. Okay, but it is still used in memory designs or other latch designs. I think this is the last slide of this one. So let's go to before the TAs come over here, let's go to the next talk. Okay, in this course, the final project that you select is called this combinational design. Okay, most of you select the so-called the adders or the multipliers or the memories. This kind of thing. What is that? Okay, now it's about time to do some so-called the teaching evaluation. 你是那个来做教学学校的 ，OK？ 因为这是学校的规定哈，所以我们要花多少？10分钟？10分钟 ，OK？ 教学意见调查你们随便写没有关系 ，I don't care because I have tenure and I'm about to retire。然后那个完了之后大概10分钟休息一下，所以现在大概是现在是20分是吧？我大概45分回来哈，你们就先做完教学意见调查，然后我45分回来喝个咖啡。OK， take a break. We stop right here. We'll be back.